Well, we are going to get into the nitty-gritty when it comes to Lewis structures and examining resonance and formal charges. So resonance structures is when there's more than one valid structure. A common, lovely example is benzene. This hydrogen should be over here, but in the sense that benzene is present, we would see that they alternate double bonds. So you have a double bond, single bond, double bond, single bond, double bond, single bond. All of these junction points are carbons. However, we would think that this would be a double bond would be shorter here and a single bond would be longer here, because that's the way we looked at bond lengths when we talked about single, double, and triple bonds back a few sections ago. But when we measured them, they see that all of the bonds around here are equal length. It's an average of the resonance structures. So it's kind of a 1.5 as far as energy needed and as far as bond length goes. So these are representative of resonance structures. So resonance bonds are shorter and stronger than single bonds. However, they're longer and weaker than double bonds. Again, like a 1.5 in the sense of that. So there's the idea that there's resonance in ozone, O3. Neither structure is correct because there's not one double bond and one single bond. They're actually identical and in between. So we need to actually show both of these when we have a resonance structure. Now on the AP test, they often will say, draw its resonance structure. They'll give you one and maybe you have to do the other, or say, here's the things, make sure you show its resonance structures. So the idea is that it is intermediate between the single and double bonds, which kind of makes sense, is that there's this bounce around that it's not quite this, not quite that, it's got to be in the middle. Now you also have this in polyatomic ions, carbonate, very familiar, acetate ions, that you have this kind of single double bond back and forth between these two. Use square brackets, double-headed arrows to kind of show that it transitions between this and that, but also make sure you have your charges shown as well. You might think, how do I come across this, that I know it has a resonance structure? Well, you might notice that it's when you have a central atom that has the same atom bonded to it in multiple ways, often oxygen, but you have this unequal symmetry, or like it could be this one double bonded, or this one, or that one. That should help give you an idea of resonance structures, of when you need them. So sometimes you also see it as a dashed line to indicate a resonance structure. I honestly haven't seen this too much, but again, you easily could, kind of representing one and a little bit more in this concept. So in any of these cases, these would all have what's called the same formal charge, because all of these are the same atom. So each oxygen is going to pull the exact same way. And this idea of formal charge is to give us the better resonance structures that are more common based upon the way attractions and electrons are attracted to things of high electronegativity. So we want to minimize the formal charge on the atoms, having the negative formal charge on the more electronegative elements, meaning closer to fluorine, and will help predict which structure is preferred. So we just look at these common ideas to where you've got a carbon in the center, and this works with the valence shells, this works with the valence shells, and so does this. However, we can see that we have a 0 here, and we'll go through how to calculate these. A 0 here and a -1, your formal charge should match your ion charge. But sulfur is further from fluorine based upon nitrogen. Nitrogen's more electronegative, so that's where the -1 should be on this, and we shouldn't really have a separation because this has a -1 charge, but this has the unbalanced areas where you want to have it limited or lowest on all of them. So let's take a look at how to actually calculate these, because it can be formulaic, but also quite confusing. So the formal charge is equal to the should, meaning the number of valence electrons, minus the lone pairs of electrons on the atoms, plus half of the bonded electrons, half because they're sharing it with another atom. All right, so this is our structure we're going to utilize to indicate formal charge for each of these elements. So atoms would like to be close to 0 as possible. So if you can do 0, that's the way to go. Any negative ones that would remain would be on the most electronegative atoms. So again, you see this over here between these two, have the lowest charge and more zeros. This one has only 1 0. Nitrogen being more electronegative would have the negative, sulfur would not. I think I had the last part there. And the sum must be equal to the overall charge. So if there's no charge, overall formal charge needs to be 0, -2, -2. So let's take a look at some of these examples here. So let's take a look at this first example here. Everything's single bonded, right? This is a possible resonance structure. And so let's count through what we have. So we have the number of valence electrons oxygens come with, 6, minus the number of lone pairs. You can count 2, 4, 6, minus half of the bonded electrons. Each have 2. So that means oxygen's formal charge, each of them, because they're all the same, is -1. Sulfur comes with 6. It has no lone pairs of electrons. And it has 8 bonded electrons, so half of that, we do our math, we get +2. Now, when we multiply all that up or add it up, it's good. It matches the charge of the sulfate ion. So this is a possibility. However, you see the negative is on oxygen, but we have non-zeros, right? We want to have many zeros as possible. So let's look at the next possibility. We have a double bonded here and only one single bonded. So we've got an expanded octet in sulfur, and you'll learn that this is kind of more common to occur. So when we look at this idea here, we go through the bonded oxygens, exact same idea for the single. Double, we get a 0. That's good. That's good. Sulfur, we go from our 6 that it starts off with, has no unbonded pairs, 10 electrons. So now it's +1. That's better than +2. And we get our sum still as 2- of adding up all the different formal charges. So this looks like a better outfit because we get some zeros. This is not as high. That's still negative, and that's the most electronegative. So good. Let's look at another example. Try to go double up, see if we can get better. Single bonded oxygen, same, good. Our double bonded oxygen should come with 6. They have 4 unshared pairs, or 4 unshared electrons. That we get a 0, bueno. And then for sulfur, we get 6 valence electrons, none in there, half of that 0. So we get 2 0 values, which is always what we want to try to get. And we have, if there is a -1, it's on an oxygen, which is more electronegative. So this is the best sulfate ion compared when we talk about formal charges. So looking at nitrogen dioxide, we've got 8 electrons. We've got, it looks like an uneven number of electrons, and we can have that. It's just generally not found too often. But of course, we're in AP chemistry, so things that don't fit the mold can occur. But when we look at the formal charges, we got good. That's more electronegative. And we got a 0. We still have a +1. Okay. Here we kind of have the same ideas, but we now have this oxygen would have a +1 based upon its number of electrons, and that's really bad because it's more electronegative. But we come down to the 0 because this is how much each should have based upon the way they're structured. So this would be the best because, hey, they're all closer to 0, no negatives. We don't have a charge, so that's why 0 works for us. So Lewis structures are this idea of the localized electron model, LEM. Just thought of being belonging to pairs of atoms when bonding uses atomic orbitals. Lone pairs only belong to that one atom. So we would normally think, that these electrons are only with this oxygen. These electrons are only with this nitrogen. And, for our simplicity reasons, that's fine and true. However, resonance points out the weakness in this, that there are other better models. Delocalized electrons are like we saw in the benzene, to where they're able to be in any area throughout there. It doesn't work with local electron model, but we know it happens. And again, this just starting to go into some things deeper that we won't really dive too deep into. But this is the idea of why we need to look at formal charges, because for every model that we've been using in chemistry, there's always something a little bit better, but of course a little more complicated. So we try to only complicate it up to a certain level each time. Let me know if you have any questions about formal charges and things like that, and I'll catch you later. Take care.